Section 32.6, Other Thermodynamic Functions. In this section, we'll talk about the Helmholtz free energy, pressure, enthalpy, and Gibbs energy. This is the expression of the average energy of particles. And this is the expression of the internal energy. The internal energy is simply the number of particles times the average energy. This uppercase N times KB is simply lowercase n times R. This is an expression for Boltzmann's entropy. And then A, the Helmholtz energy of the system, is equal to U minus Ts. So we have this minus temperature times this. The final expression is negative nRT lnQ. So the expression for the Helmholtz free energy of the system is simply negative nRT ln Q. And Q is the product of the translational partition function, rotational partition function, vibrational partition function, and electronic partition function. Let's focus on ideal gases. If we assume the system is an ideal gas, and then we have this translational partition function, rotational partition function for linear molecules, rotational partition function for nonlinear molecules. This is vibrational partition function for linear molecules with 3n-5 vibrational modes. This is the vibrational partition function for nonlinear molecules with 3n-6 vibrational modes. This is the electronic partition function, assuming most atoms or molecules occupy the lowest electronic state with a degeneracy of G sub 0. So when you have a singlet electronic state, G sub 0 is 1. Doublet, G sub 0 is 2. Triplet, G sub 0 is 3. So now we can expand the expression for Helmholtz free energy. It's negative nRT times the sum of these four logarithms of Q trans, Q rot, Q vib, and Q electronic. What you need to do is you just need to evaluate the translational, rotational, vibrational, and electronic partition functions for a system, and then plug in those numbers. And then you will obtain the value of the Helmholtz energy of the system. Because dA is equal to negative SdT minus PdV, we know pressure is negative delta A over delta V. This dA over dV when temperature is constant. So when this dt is 0. Therefore, P is equal to nRT times, well, the first derivatives of this guy plus this guy plus this guy plus this guy. Now I want to remind you the rotational partition function does not depend on volume. The vibrational partition function does not depend on volume. You don't see volume here. And then the electronic partition function does not depend on volume. Again, we're talking about ideal gases. All right. So for ideal gases, only the translational partition function depends on the volume. So this will become 0, 0, and 0. You just need to plug in the expression of the translational partition function. It's right here. And also, you just need to look at this, how this depends on volume. Therefore, pressure is nRT times the first derivative of the logarithm of the translational partition function with respect to volume when temperature is constant. So now I plug in the expression of the translational partition function is right here. And the logarithm of a product of A and B is the logarithm of A plus the logarithm of B. So we can separate the logarithm of V from all other constants. We are treating temperature as a constant. So really over here, this is just the first derivative of the logarithm of V, and that's 1 over V. And then we have pressure is equal to nRT over V. This is the ideal gas law. Now let's derive enthalpy and Gibbs energy. So over here we have the expression for U, we have the expression for entropy. We have the expression for Helmholtz free energy. I want to remind you these three equations can be used for all matters, not just ideal gases. It's just for ideal gases, it's easier to compute its translational partition function, rotational partition function, vibrational partition function, and electronic partition function. You can use these three expressions for liquids, solids, and real gases. It's just more difficult to obtain the expression for Q. Now H is U plus PV by definition, and therefore this is the expression for H. G is equal to A plus PV, and therefore this is the expression for Gibbs free energy. So now you have these 5 equations. They are exact equations, and this Q is the product of Q trans, Q rotation, Q sub vibration, and Q sub electronic. If you have a monatomic ideal gas, and then this Q is simply the translational partition function multiplied by the electronic partition function. And this expression is based on the assumption that the gas is ideal. If you have a linear molecule that behaves ideally, and then you need this translational partition function, rotational partition function, vibrational partition function here, and then electronic partition function here. For nonlinear molecules, we need to modify the rotational partition function. Now it contains this 1, 2, 3 terms. They correspond to the rotations about the x, y, and z axis. Over here, this is the vibrational partition function for a nonlinear molecule. And finally, this is the electronic partition function. So again, these 5 equations are general equations. You can use these 5 equations for all matters. It is just a bit more difficult to obtain the expression or value of Q for real gases, liquids, or solids. And finally, I want to mention this. This equation is a little special. So if you look at this equation, S is a function of Q, and in this equation, Q is slightly different from the Q in the expressions of U, A, H, and G. Why is that? In the expression of entropy in terms of Q, the partition function Q, this Q, is calculated having the 0K internal energy as the zero reference for energy. So when we are deriving this, make sure when you calculate this Q or derive the expression of this Q, you need to assume the 0 point vibration energy is 0. The 0K electronic energy is also 0. And then you will get the value of the entropy of the system that's in accordance with the third law of thermodynamics. So again, I want to show you the equation for Q. This is monatomic ideal gas, linear molecules, nonlinear molecules. Those are the expressions of the partition function. And once you have those partition functions, you can plug it in here. You get this Q of all motions of nuclei and electrons. And plug in this Q in here, 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 and here. You will get the expressions or numerical values of the internal energy, entropy, Helmholtz energy, enthalpy, and Gibbs energy.